when everyone has found a seat, we'll begin, but just in the meantime, we've got a lost glove already, and I think it's leather, so if you... Oh, okay. Oh. Thank you. Okay, I'd just like to start. My name's Serene, and I'm the school captain at Cherry-Brook Technology, and this is Matt, the male school captain, and we're just going to be your host and hostess for tonight. We'd just like to start with welcoming you all very warmly to our school tonight, and it's great to see a really great crowd here who are really enthusiastic about finding out about science in this area. And there's going to be a lot of exciting things tonight from a lot of different people speaking and a lot of different types of visual presentations that you'll see tonight, and we really hope that you'll enjoy that. Just passing on to Matt now, he'll introduce our first speaker.
Hello, I'm Matt. Just a quick reminder that although tonight we're not doing the cosmos, an astronomy night will be held on the 29th of August where we will be doing that, and I've been told there'll be lots of big telescopes. Now we have Mrs. Wentman, who's going to give her principal's introduction.
I feel like it's assembly again. Now it's Mrs. Wentman going to make her principal's speech. I'm really here to just, again, warmly welcome everyone who's here. You're here in the second day of a big week for us. Some of you won't be here again, so I'll just let you know what we're doing. Last night we had a very big dinner and a very successful dinner to launch our technology week. Tonight, of course, it's the astronomy night's turn. Tomorrow we've got a business breakfast at 7 o'clock in the morning, so there'll be some of us here very early. I believe there's some students coming at 5:30 tomorrow morning to get our breakfast ready. And then we've got speakers talking about the year 2000 bug and all sorts of things like that. During the day there are conferences and seminars, and tomorrow night we're putting, we don't know how many, but a lot of computers in this hall, and the students from the school are going to be able to play computer games tomorrow night. So if you live in Cherry-Brook and your lights dim at about 7 o'clock, or worse still if they go out, you'll know who's to blame. It's us. And then over the weekend there's more seminars. On Monday there's some professional development activities for teachers. And if you are around and you want to come back, next Tuesday is really going to be a fantastic day. Next Tuesday from 3 o'clock until 9:30 in the evening is going to be a trade fair in this hall with about 20 different displays, companies displaying and selling their products, all sorts of hardware and software that you might be interested in for your children, for education, for use in the home. Lots of displays. All of the subjects are going to show how they use technology in teaching. And for older students, we're having a seminar on careers that might be available in the computing and the information technology area. So as you can see, it's a big week for us. By next Wednesday, we'll be all exhausted. But that's in the future. Tonight is what you're here for. And tonight we're very, very fortunate to have two very renowned speakers come to explore with us and explain about the heavens. If you've been to one of these evenings before, the slide images are usually just incredible. So there's a lot to do and a lot to hear about, and I'm not going to waste any more time. So once again, welcome, and I'll pass back to Matt and Serene.
Thank you, Mrs. Wentman. Tonight we have an interesting program where you, the audience, are involved in our question time segment. We also have two guest speakers and various presentations. And there will be an intermission at approximately 8:15. Finally, we hope you have an enjoyable night. And to start things off, we have our first guest speaker, Professor Marcus Price, who has a background in physics, mathematics, and radio engineering. At present, he is the director of the Parkes Observatory and will be presenting around the world in 30 minutes. Mr. Park.
Lights coming on, and I'd like the lights to go off. The light guys were here a minute ago, and we've got to turn can probably hear better. Isn't technology great? Okay, here we are looking at a typical optical observatory. They put them on the top of mountains, of course, to get above as much of the pollution and the air mass as possible. But at the same time, you want to get away from the clouds. So often you find these observatories in desert climates. And as you can see here, this mountaintop in Chile, in South America, is typical of many of the first-rate optical observatories around the world today. Here in Australia, we have a lot of desert, but we don't have many high mountains. Our highest mountains here in the eastern part of Australia are found up in the Wormhole and near Coonabarabran is where the observatory, the Anglo-Australia telescope is operated, and also the Mount Stromlo facilities are there, the ANU, and Fred Watson may say a bit more about that later on. But what I want to talk about mostly tonight is radio astronomy. This is the 64-meter radio telescope at Parkes out in central New South Wales. The diameter of the dish is 64 meters. Again, it operates the same as a optical telescope. Light comes down, or the radio waves actually come down, bounce off of this parabolic shaped reflector, and up here to the focus cabin, where we then capture the radio waves, first in a apparatus we call a feed that really looks like kind of a big tin can. And inside that tin can we have a little wire dangling down, and the radio waves are caught in the tin can and forced to go down this wire and inside of a radio receiver. And the radio receivers are not a whole lot different than the one you find in your car, except they're much more sensitive. They're about 1 million times as sensitive as the one you have in your car. And partly that's because they are cooled to very low temperatures. The receivers inside this focus cabin are kept at a temperature of about 250 below zero. And the reason we do that is because the electrons, the current, electrical current inside of the receiver tends to wiggle around a lot and cause static when you don't keep it cold. That's why you get static on your car radio between the stations, sort of a hiss. We don't want to hear that when we're listening to the cosmos. So we keep these receivers at temperatures about 250 below zero. These receivers are also very special in that we now on Parkes have arranged it so we can look at 13 different regions in the sky simultaneously. We don't just look at a single region, but at 13 different regions. And that's what makes the Parkes radio telescope today, even 40 years after it was built, the world's most powerful single-dish radio telescope. But there is a disadvantage in radio astronomy to having only a single dish like this. So many times, if I can go forward instead of backwards, many times today, and here in Australia, we now have a multi-element radio telescope where we have 6 telescopes. The 6th one you can't see because it's about 6 kilometers away from the rest of these. But we use multi-element radio telescopes to give us better resolution or better image sharpness. And again, these telescopes, all developed by the CSIRO, both the structural designs and the radio designs. And this is what makes Australia one of the leading countries in the world in radio astronomy, is this tremendous amount of technology we bring to bear on all of these questions. Now, these signals that we collect in these multiple radio telescopes have to be processed, and in fact, it takes a very sophisticated back-end, as we call it, or computer. These racks that we put our radio signals through after we receive them are essentially supercomputers, nearly as powerful as the most powerful supercomputers in the world, except they're kind of dumb supercomputers. They can only do one thing. They can add one signal to another signal very, very rapidly, and that's what we specially designed them for. And they're only useful, they couldn't help you with your homework at all. They're too dumb. But they can add radio signals together very, very rapidly. Now, as I said, you like to use multiple telescopes to get a good image, and so what we're now doing is combining the images from Narrabri, Coonabarabran, Parkes, and the space station at Tidbinbilla together those from the University of Tasmania down in Hobart, and we get the effect as though we had one telescope that was as big as all of eastern Australia. And in fact, we sometimes put our telescopes together with those in North America, particularly the Hawaiian one, because we can't see the same part of the sky that the guys over here in eastern United States can. But when you have all these telescopes hooked together in a giant array, it's the same as having a single radio telescope that is as big as the entire Earth. So this is how we get image sharpness in radio astronomy, and many of the images I'll show you later on today are of the type that can be made with radio telescopes of this type. Okay, I still have some yellow lights up here that are looking at me. Can we turn those down, please? You don't need to see me. I'll be here at the end of the talk still. Now, this is just an artist's impression that I use to remind me that now is when I should start talking about the Big Bang. And the reason this reminds me of the Big Bang is at the moment of creation of the universe, at a time we estimate to be some 15 billion years ago, there was a tremendous explosion and our whole universe came into existence in a fraction of a second. And in the first few seconds of the universe, it was so extremely hot that matter could not exist and energy in its common forms did not exist. But it was a soup, sort of a combined soup of matter and energy. And that's what this painting reminds me of the, if I can back up here, the single points you see here are when it's in the matter stage, and of course the fuzzy lines show you when it's whizzing around being heat energy. So that's what it was like for the first few seconds of the universe. Tremendous amount of confusion, chaos, and extremely high temperatures. But as the universe expanded at the speed of light, it cooled off very rapidly. And within a period of a few million years, it was cold enough that stars could begin to form. And indeed, stars did form, and this is an optical picture of the Pleiades, a nice star group, in which you see new stars that, I keep pushing the wrong button here, sorry about that, in which new stars have just been formed and are blowing away the gas clouds out of which they formed. And I'll say a bit more about that in a few minutes. Stars, as you notice, like to come in groups. The Pleiades is half a dozen stars. Here we see a star cluster that perhaps has a few hundred, and there are other star clusters out there in which you find as many as 1 million stars in one single star cluster. And I remind you, it's not static like this. All of these stars are whizzing around each other. They're essentially all in orbit around the central mass concentration, but mostly in highly elongated orbits, as I'm indicating with the pointer. Of course, they don't move quite that rapidly. Typically, it would take them something like 100 million years to make the sort of loop that I'm showing here. So if you could see these, a motion picture of these clusters, they look like a swarm of angry bees, essentially, buzzing around each other. This is what we call a globular cluster, and indeed they're a beautiful sight to see. When you come back for Astronomy Night in August, you'll be able to see some through the telescope and appreciate some of the wonders of the southern sky. Now, we're not quite sure whether the stars formed first or whether the galaxy masses formed first. But we do know that about the same time that stars became a predominant part of the mass distribution in the universe, that we had concentrations of these stars into what we now call galaxies. Now, a galaxy, in this case, a spiral-type galaxy, consists of anywhere from a few million stars up to hundreds of billions of stars. And these billions are the Carl Sagan American-type billions, which that means 1,000 billion. So you almost have, in some cases, close to 1 million stars in one of these galaxies. Now, these galaxies aren't all the same. In fact, each one is different. They're just like people. They all have their own personality. They have, you find spiral galaxies like this one. you find barred spirals. That is to say, they are a spiral form, but they have this central bar that joins the spiral features. And you also have the giant elliptical galaxies. And to give you a feeling for the scale for this giant elliptical galaxies, you see these points around here, these individual things that look like bright stars. Each of those points, in actual fact, is one of those globular clusters with over 1 million stars in it. That gives you an idea of the scale of these giant elliptical galaxies. And you notice even the galaxies tend to come in groups too. Here you find, oh, I pushed the wrong button. There's too many buttons here. I'm the same way at home when I'm trying to watch football on television. I keep changing the wrong channel. Okay, now here are the little guys hanging around, sort of like dogs out for a walk with the big galaxy. And it's very common to find these smaller galaxies in groups around these giant galaxies. And in fact, we think these small galaxies are sometimes what excite the gas in the larger galaxies to go into the spiral forms. But I haven't got time to tell that story tonight. Here is one of the spectacular pictures that's been taken from the Hubble spacecraft. Of course, those of you who, and particularly Fred, it's very embarrassing to have another professional astronomer around when you do things like this. This slide is in upside down. So, of course, I make up for that by pointing out that I'm from North America, and seeing from up there, this is the right way, up, of course. But anyway, the Hubble Space Telescope, which is a very large orbiting telescope that's above the Earth's atmosphere, is able to take extremely sharp astronomical images. And this is one of the beautiful pictures that's sent back. It's even better when it's right side up. But the important thing to notice is that in the cosmos, you find many regions like these fingers of these pillars of Hercules, as this formation is known, where you have a lot of gas, hydrogen gas. Hydrogen is the most abundant element in the universe. All of the hydrogen gas was made within the first 3 minutes of that Big Bang, and there hasn't been any made since. So starting with that building block from the first 3 minutes, we now have to make all the stars, and this is how we do it. This hydrogen gas collapses into compact clouds under its own self-gravity. Gravity, you all know, that's what's holding you in your chair right now, and the reason that I don't fly off into space when I jump. Okay, and gravity acts not only on people and chairs and cars and things like that, but it acts on gas. Every gas particle, every little bit of hydrogen out there in the universe can feel the attraction of every other little bit of hydrogen gas in the universe. But the closer the little bits of gas are to each other, the stronger they pull on each other. So when you have gas that starts to collapse into a cloud, the forces are extremely strong, and it pulls these molecules together, or atoms closer together, and pretty soon you have dense clouds. And in fact, inside these clouds, it gets so dense that sometimes the temperatures rise to millions of degrees. And once the temperatures rise up to millions of degrees, you get a process called fusion. And the fusion process simply is one where the very hot atomic hydrogen particles bump into each other so hard that they stick and they fuse together, hence the name fusion. And in the process, you convert hydrogen gas into helium. And helium, it turns out, a bunch of helium weighs less than the constituent parts of hydrogen that went together to make it up. That's to say, when you put hydrogen together to make helium, you end up with helium plus a little bit of leftover mass. And that mass is in the form of energy. And what that says is that you end up with a bunch of helium gas, except it's now really, really hot. And you have the heat pressure pushing one way on these clouds. You have the gravity pushing the other direction, trying to collapse the clouds. And what happens is every now and then that stabilizes, and out pops a star. So it's even in these regions of high gas density that we find our stellar nurseries. These are the places where stars are being born. And in fact, right up here inside the tip, it's beginning to glow a bit, and there may be another star just about to pop out of there. So these are stellar nurseries. This is the site of stellar birth in our own Milky Way galaxy. And in these clouds, interestingly enough, when these stars come out, blow away the gas from around them, and have formed in stable star systems, they evaporate the gas from the edge of these clouds and leave the high-density gas in here to form more stars. And I might point out that much of what's in there, you notice it looks dark. That's because it is dark. There's a lot of dust in there as well. Particles of carbon and silicon, or ice-coated particles, sort of interstellar pollution, if you will. And it's in these dark clouds that you have a lot of molecules as well. We now know of more than 100 different molecules that are found in these interstellar clouds. And most of these are biologically active molecules or carbon chemistry molecules. Things like alcohols, acetylene, formic acid. We think even we have found glycine. Glycine is the most basic amino acid found here on Earth and in living systems. So within these same clouds, the stars form from and the planetary systems form from, we have the precursor chemistry for life. And in actual fact, we now know of several stars where we can see a disk form around these stars. Here we've used a special filter to block out the starlight so that we can see the actual optical light coming from the disk around this star, and it's within that disk the planets are forming, we believe. And it's on those planets then that these biochemicals may be deposited, and we may end up with seeing basic forms of life evolving on those planets ultimately. Now, some stars, when they form, instead of just blowing away the gas in a nice uniform way, if they're extremely massive stars, say 10 times or 20 times as massive as our own sun, as they're blowing away the gas clouds they formed out of, they seem to blow them off in preferential directions. And in fact, this particular young star called Eta Carina appears to be exploding, but in actual fact, there's a nice young hot star in the center here that's just driving away all the gas around it in a rather strange pattern, perhaps due to the fact that the star is spinning and there's a disk around here, and also the fact that there may be some very strong magnetic fields in space there too. Now that we have the Hubble Space Telescope up, and now that we have very long baseline interferometry giving us extremely precise radio pictures, we're learning more and more about these very strange objects that we see like this in our telescopes. Well, once a star is born and starts to burn its hydrogen gas, it goes along happily for a number of millions of years typically. Here again we see another case where a bright young star is just forming inside of this cloud of gas, and you can see that the star illuminates the gas and causes it to glow. And the characteristic colors you get from the hydrogen gas around these stars is reddish, or in some cases you'll also get a blue tint to it as well. These are close, not perfect, but very close to the actual colors that that are associated with these regions. Now, your eye wouldn't see them this brilliantly because these are very, very faint clouds. And when you look, a lot of people are disappointed when they look through telescopes because they don't see bright, beautiful colored things like that. But again, the trouble is it's very faint, and so you need to integrate. Again, that's why we need film or electronic devices that integrate a long time to bring out these beautiful colors. Now, I'll skip the boring part of a star's lifetime because for most of the life of a star, just like our sun, it just sits there and glows. Well, that's great if you happen to live nearby, but pretty boring if all you want to do is study stars. So stars like our sun, for instance, live about 10 billion years. Heavier stars, that is to say ones that are 10 or 20 or 50 times as heavy as our sun, may only live as short a time as 1 million years. And then they blow up. Some of them blow up in a gentle sort of a way, That is to say, this one formed what we call a planetary nebula. The star that's left over is right there in the center. And in fact, it was munched in the explosion. When you think about it, if an explosion blows outward, some amount of force has to blow inward as well. So that's what happened to this star. You ended up with about one solar mass scrunched down into a planet-sized sun, now about the size of the Earth. So that's about the size of the Earth, but it has the whole mass of a sun. But now it's about 100,000 degrees in temperature compared, say, to our own Earth, our own sun, that's only about 6,000 degrees in temperature. And of course, all of the stuff that was blown off out here forms a beautiful ring around this, and what we call a planetary nebula, not because it has anything to do with planets, except the fact that when you look through a small telescope and see this kind of greenish, bluish thing in the sky, it looks a bit like a planet. So they call them planetary nebulae. So this is what happens to stars that are a little bit heavier than the sun. If they're a lot heavier than the sun, they just go completely bananas and blow up completely in what we call a supernova. And in that case, essentially all of the mass of the star gets spread over the heavens and leaves only a very small region behind, a very small star, again about the mass of the Earth, of the sun, or a little bit more in some cases. But again, the power of the explosion behind the supernova is so powerful that we can't see the residual or the remaining star that's left behind, because that star is so small now, it may only be a few kilometers in size. A few kilometers, that's less than the distance from here to Ural or something. It's not very big, but you've got the mass of a whole sun in a region only a few kilometers in size. And in actual fact, in some cases, it's squeezed down to even smaller than that, where it's just 1 or 2 kilometers, and then it becomes a black hole. And I'll talk a little more about black holes later on. So these supernovae are very important. For one thing, they recycle gas back into the interstellar medium. And this is not the hydrogen gas we started with, because remember, it's been fusing. And first it fuses or burns into helium, and then the helium burns into carbon and nitrogen and oxygen, and essentially forms all of the elements, the natural elements that we find in the universe are forged essentially inside of stars, and in particular in the last few seconds of the lifetime of these supernova explosions. And that's why they say that each of us is made of stardust, because the oxygen, the phosphorus, the iron, all of the heavy elements in your body had to have been forged in the heat of a star, the center of a star, or in a supernova explosion. So, you're star stuff. And again, this matter that is recycled into the interstellar medium slowly but surely goes off and joins other clouds of hydrogen gas, so that you have enriched hydrogen gas then that can form new stars and new planetary systems. Now, this is an artist's impression of our Milky Way galaxy where we live, and of course we can't get outside of our galaxy and send somebody out there with their Instamatic to take a neat picture, so we just draw a picture like this to give an idea of what our galaxy is like. We're out here in the galactic suburbs. This is kind of like Ural and this is Sydney, if you think of it that way. And that's just as well, because of course close to the center of the galaxy there's a lot more radiation. And so it wouldn't be very comfortable there. We'd probably fry. So it's just as well to be out here where it's a little quieter. And most of the stars you see in the sky, in actual fact, are within the region of the box that's shown there. You don't see stars much further away than that in the night sky. So you really don't, optically, you don't see all the rest of the galaxy. But radio waves can go through all of these arms, through all of the dust and the gas, so that with radio telescopes we can see the center of the galaxy. We can see these gas arms, the hydrogen gas that makes up these arms. And it's within those arms where you have extra hydrogen gas that new stars are being born all the time. The stars in between the arms are the old red stars. They're not very interesting again. They're the ones that live for tens of billions of years and just kind of sit there and glow. But out here in the arms, that's where new stars are being born. That's where you have supernova explosions. It's where you have all the action in the galaxy. Well, now if we're going to get to the edge of the universe and back in the next 10 minutes, so we better go. Again, we move away from our own galaxy out to the realm of other nebulae. And again, I show you another spiral galaxy just because they're so incredibly beautiful. But I remind you that they're made up of stars that are in arms that are made up mostly of gas, the hydrogen gas. It's very important to note that these arms are, what you see here is the hydrogen gas that's being caused to glow by all the bright young stars that have been born there. There are equal number of stars out in these regions to what are in these arms. But the stars out here are the old red stars, so you don't see them. Young blue stars are in here. They were just formed in this hydrogen gas, and now they're causing the gas itself to glow. And you can also see evidence for the pollution, the dust, particularly along the inner edges of these arms. You see regions of dust. Dust plays a very, very important role in the interstellar medium and in the formation of stars in our galaxy. So we move away from the Milky Way, past another one of these giant elliptical galaxies, where we find very exotic processes going on in the center. If I back up for just a moment, again, one of the things about a galaxy like this is it doesn't have much gas in it. That is to say, you do not have star formation going on inside this galaxy anymore. It's eaten up all of its gas, but in the process, it has become very concentrated toward the central region. And in actual fact, we believe that at the center of all of these giant elliptical galaxies, and perhaps at the center of every galaxy in the universe, there's a black hole. And these black holes have a very high gravitational field. And this gravitational field then pulls any gas and some of the stars in here down toward the central region, basically eats them up. And of course, after you've had a big meal like that, you tend to burp. And those burps are in the form of giant radio wave or giant plasmoids that give off lots of radio waves. Here's a picture of a radio picture of a giant elliptical galaxy. In this case, the optical picture of this galaxy would look about like this, be about that big, very bright, and that's all you'd see. But from this central region, we see giant burps, as I call them, or giant radio jets being shot out into space. Hundreds of thousands of light years. Now, I haven't used light years up until now. Light year is the distance that light travels in 1 year. Now, that's a long ways, because if you think about it, it's taking the light from me to reach your eye. Right now, it takes about 20 billionths of a second. Whereas in the case of these jets, it takes light about 100 million years to go from one end of this jet to the other. So you have these tremendous jets of radio energy and plasma being shot out into space from the interactions that are going on close to this black hole in the center of this galaxy. And indeed, even though the optical light is concentrated to the stars, the radio energy is shot out in these giant plasmoids, and that's what allows us to study a different kind of physics. In fact, the optical astronomers, just looking at the nice quiet stars, had no idea that all this violence was going on in the center there with these black holes. And in fact, there's even more violence in some stars or some galaxies that we call quasars or quasi-stellar galaxies. This is a whole galaxy here. Now, it looks just like a star. This is a star image here. That's a star image. But in this case, instead of having nice spiral arms and all that, this looks like another star. And the reason is because it's so incredibly bright and so small that you can't see the detailed structure around it, because the brightness coming from the single point of light in the center blinds you to the rest of the spiral structure that exists around this. Now, the only clue there is that this is a special object is this little jet. Again, a jet of radio energy, and in this case, some optical energy too, being shot hundreds of millions of miles, or I should say light years, into space. So these quasars are the extremely powerful radio sources we can see clear at the edge of the universe. And here's another example. Again, you would see a galaxy about this size. Right in the center is where the black hole is, shooting these giant jets out, causing these radio plasmoids to be formed in space. We can't see the jet going the other direction because it's being shot away from us. And because of some of the oddities of relativistic physics, when particles are being shot toward you, you can see them very clearly when they're being shot away from you because they're moving so rapidly it's hard to get a good view of them. So this is how we can tell that the bottom jet here is coming toward us and the top one's being shot away from us. Again, these are typical of the images we make of radio galaxies these days. And now that we have the Hubble Space Telescope, again I have to go back to my optical friends for help here, we're able to focus down inside of one of these elliptical galaxies. And I should explain right here, the white light is the giant elliptical galaxy. The yellow light you see out here, the reddish yellow, is the plasma jet. This is a radio picture, the outer parts, optical picture in the center. And it forms what we call then, now in the last few years have been able to take detailed pictures deep down inside of this optical giant elliptical galaxy, and we can indeed see the gas disk, and right down there in the center is where the black hole is. Up until last year, I always had an artist's impression of this, saying this is what we think is at the center of all these galaxies. But now, thanks to the Hubble telescope, we know that indeed there are some giant galaxies, black holes, right there at the center. Now, I should stop for a minute and talk a little bit about what a black hole is. Now, by black hole, typically people think of some area where you have extremely high gravitational fields and extremely dense matter. It needn't be that way, but let's think about that for a while. If we had a black hole with the mass of the sun, as I said, it would have a diameter of about 3 kilometers. And if I would stand on this black hole, as I'm standing here on the Earth, I could juggle a ball. And now I'll do this for just a moment, if I can put down the microphone without dropping it. And I don't require too much technology. But I think you can see well enough, even in the darkened conditions, to see that if I throw this ball up in the air, it follows a parabolic path and comes back down. And that's because, you know, unlike some of the fast bowlers, I can't throw the ball fast enough to make it escape the earth. If I can throw it fast enough, high enough velocity, I can throw it essentially away from the earth and it will never come down. But even on the black hole, I would still be able to throw this ball back and forth. I mean, I actually crunch to get it high, I think is the current popular term. But the point is, it's ordinary gravity right at the surface, or the event horizon of the black hole. But now the lights are off now. If I took my flashlight, which I'm sorry isn't very powerful, but you can see that here on Earth, the light traveling at the speed of light, 300,000 kilometers every second, that it escapes the gravitational force of the Earth. Because don't forget, light is energy, and energy has the equivalent form of mass, right? Remember, E equals mc squared. Einstein's famous equation that says light and energy are the same thing. Mass and energy. Mass and light energy essentially are equivalent. So even though the Earth is pulling on this light and trying to make it fall to the Earth like a ball, it doesn't do it. If I take my light to the black hole and I shine it upward, in actual fact, what will happen is it will do just what ball did. The gravity will cause it to follow a path, a parabolic path, and it will be trapped into the black hole. And simply what that means is that no light can escape from the black hole, and that's why the black hole looks black. Because no light or any other form of energy can escape from a black hole. So it has to appear black. And of course we add the whole bit to it just because anything that you toss into a black hole disappears. Like if you've thrown it in a big hole and you can't get it back. So we believe that at the center of all of these galaxies, that there is indeed a black hole, and that black hole is providing the energy to drive these very powerful radio sources. Now this is the most distant image that we've ever taken toward the edge of the universe. That is to say, all the images you see here are galaxies. Thousands of them. Every one of those little dots is a galaxy. In fact, even this is a very, very bright galaxy, I believe. I could be fibbing. That might be a foreground star. You know, to take these deep pictures, we have to look out through the galaxy, our own Milky Way galaxy, and if there are any stars in the line of sight, we see them. It's kind of like having a dirty window in front of you. But when we look toward the edge of the universe, we see thousands of galaxies out there. And these galaxies were formed not all that long after the beginning of the universe. And the great mystery today in astronomy is to try to understand how these galaxies formed, exactly whether they formed just before or just after the stars in them formed. In other words, did the stars form and then coalesce together to form galaxies, or did the gas fall together to form galaxies and then the stars formed in that form there? And the answer is we don't know that yet. But this is the great mystery, one of the great mysteries we're working on today in astronomy. The second is the question of mass. I think you've all heard of the mystery of the missing mass, or the dark matter in the universe. When we study the motions of galaxies and the gas and dust in galaxies, one of the things we notice is there seems to be a lot more mass there than we can see. In other words, we can see the stars and we can see the stars moving, but the number of stars we count isn't as many stars as we need to account for motions. And so we know there's a lot of hidden mass out there, a lot of dark matter. And in fact, it may turn out that light matter is only 1% of the total mass of the universe. So the pictures like this of these distant galaxies, in actual fact, may only be the froth on the top of the total matter that makes up the universe. We simply don't know, but that's, again, one of the big mysteries today that we're working to solve. So we can turn on the lights now. I got us to the edge of the universe. It's going to be a bit of a jerk because we're going to come straight back from here. We're not going to stop anywhere on the way. But we can take a few minutes for questions. I think I'm probably... I'm a professor, which means I talk in 1 hour chunks, so it's hard to get you to settle down in 35 minutes. But I think we probably have time for a few questions. And of course, if you don't, you can ask your questions during intermission, and then if you want the right answer, you can ask Fred later. Oh, there was one other thing I find that very helpful after a talk like this. Some people get a little bored, like to sleep. I suggest you put your hands above your head. Okay, take your fingers, crunch them back and forth. That's it. Get that circulation going. Now, very slowly. This is kind of a rolling exercise. Move your hands back and forth. That's now. Faster and bring it down in front. Thank you. I do like to appreciate audience.
Before you pack up, Professor, we'd just like to thank you for being here tonight. It was just really great to find out what's happening beyond anything that we can see. And I guess everyone here would be able to say with me that it's pretty amazing, and we can only thank you for the opportunity that you did give us here tonight. We would like to, on behalf of the school, offer you a gift, just in appreciation. It's not every day that we have a professor here in Cherrybrook, so now we'll give you the opportunity to ask him any questions that you would like about what he's spoken to us about or about the universe. And Matt's down here with the microphone, so if you'd just like to raise your hand if you have a question.
Professor, with all that dark matter out there and all that light matter, how much vacuum is out there when you go up in a a shuttle.
How much vacuum is out there? Well, in actual fact, in most of the universe, you will not find more than one hydrogen atom in several cubic meters of space, and the rest of it is just space. Now that's millions of times less dense than the best vacuum we can produce here on Earth. We do a pretty feeble job actually producing vacuums in our vacuum chambers here on Earth, or even in near space out towards the sun. In the region of the sun, you have one or two atoms in every cubic centimeter. So as you get further away from the Milky Way galaxy, the vacuum we estimate is something like one particle in several cubic meters.
Would you be able to go through a black hole if you had a craft strong enough to do it?
We don't believe that indeed you can go through a black hole. First, of course, there's this problem with the spaghettification as you get close to the black hole. Because see, when you get close to the black hole, what we call the gravitational gradient, or the amount of gravitational force pulling on you, changes very rapidly because it gets much, much stronger as you get close. And so that means your feet feel a very strong gravity slightly before your head does. And so the effect is it stretches you out, and hence the name spaghettification. So by the time you get into the black hole, you're already probably in pretty bad shape. But just in case you survive that part, we have no idea what goes on inside of black holes. Our physics, our mathematics just simply can't tell us. It predicts that everything is smudged down. Smudge is a scientific term that means all crunched down into a really tiny little singularity, we call it, where all the mass that falls inside the black hole ends up in a little singularity that's smaller than the hangnail on your little finger. And that, of course, we don't understand what that really means, but we talk about it anyway because it sounds good. But no, so that's what we don't know what's going on inside there. Now, it has been predicted that in some cases you can have what we call a wormhole form, so that the stuff that goes into the black hole here comes out of some other kind of white hole or something over there. But the trouble is, with that, it gets stretched out. This wormhole gets very tiny, and it gets so small that we believe it gets pinched off, not by gravity now, but by quantum mechanics. That's another fancy word we use in physics that just means things are all kind of wiggling around in a funny way and you can't predict it too well. But we think, if we could predict it, that wormhole would be closed so that indeed you could not get through it. I mean, I don't care what the people on Deep Space Nine tell you, wormholes really don't work very well. So I think that's the answer. But I've never been inside a black hole, so I can't say for sure.
How many stars do you think there is? How many stars do you think there is?
My American ears don't always speak Australian. How many
Stars.
Oh, how many stars? Oh, thank you. Well, it's very difficult to make a good estimate on this. I might even call on Fred to get his idea on this. We think in our own Milky Way galaxy there are a few 100 billion stars. Now, we also know that there are billions of galaxies out there. So if you can multiply a billion by a billion, that'll start to give you an idea of how many stars there are. That will essentially be a one with about 20 zeros after it. That's how big the number is. And I don't know what they call a one with 20 zeros after it. It must be a squig million or something. But there are lots of them. If you go out at night here in Sydney and look up at the sky, you can see a few hundred stars. So what you want to do is get your parents to take you on a picnic sometime, go out to the country and stay after dark, well away from the city on a nice clear night, and then when you look up at night, you'll be able to see several thousand stars. plus, of course, the beautiful Milky Way. At night, on a very clear night, you can see about 3,000 stars with the unaided eye. If you take along your binoculars, then you can see a lot more. Or come down here in August for astronomy night, look through the telescopes, then you can see a lot more. You can see thousands and thousands of stars in the Milky Way and in galaxies. Why shouldn't there be another Big Bang out there? Well, some of our theories say that indeed there are lots of Big Bangs going on all the time, but they're different universes and we can't be in touch with them. There's no way that we can know. Our theories say they might be there, but we have no way of knowing whether that's true or not. Some people say that our universe is just one bubble in what you might say is a cauldron of boiling stuff that the whole hyper-universe is made of. And our universe is just one little bubble in that. There are lots of other bubbles out there, just like boiling water all the time. You know, some of them burble and break and do all sorts of chaotic things. But again, that's pure guessing. Now, question back here.
Professor, the universe is just so big, and we are just so small. What benefits come from studying the universe?
Well, one of the benefits, and I don't mean this to be too glib, is it helps us realize that it's very big and we're very small. Now, astronomy is a very basic research, and you might say, well, hey, what good does it do me? You talked about all these great things CSIRO is doing for the country and the world. You know, how does astronomy help? Well, for one thing, we're naturally curious. I mean, we're in a multi-purpose center of a great seat of secondary education. We value education. We value knowledge. We know that it's important. Now, some people get a little worried. They say, hey, it costs a lot. Why do we put so much money into education? Well, if you think education is expensive, figure out how expensive ignorance is. So, we like to learn things. We like knowledge. We like to share our knowledge. And so learning about the universe, it's our environment. It's where we are. It's what we're part of. And we want to learn from it. Now, at the same time, all of these technological advances I've talked about that help us see to the edge of the universe and understand some of these very, very important astrophysical questions, solve some practical questions on the way. Distance measuring equipment, which is used on all airlines and particularly for private pilots, was developed at the radiophysics laboratory of CSIRO, the same scientists who developed that 64-meter radio telescope. The international standard for microwave landing systems, again, so you can take off and land in the fog at London or wherever you are around the world, developed by the CSIRO scientists at the Division of Radiophysics, the same people that do radio astronomy for you. When you make a telephone call and it goes up through one of the fancy Telstra satellites, the shaped beams on those antennas were developed by the CSIRO scientists at the Radiophysics Laboratory, the same ones that the rest of their time do radio astronomy. So it isn't just an idle pastime. In other words, it's very important to us. And of course, I love astronomy, but I love electromagnetics too. I love to design feed horns. You know, I love to mess with understanding how radio waves work so that indeed you get better television reception. And that HD TV will become a reality one of these years in this country. But along the way, I also love to learn about the universe. And I love to share it with people. But the answer to your question is because we're curious, we want to know what's out there. Excuse me for the editorializing for the rest of it. That's another thing about professors. Once you wind us up, we're hard to turn off sometimes. Okay. I think the man here has said that that's all the time I get, but that's okay. You can catch me at intermission, or like I say, ask Fred. That's the answer to all your rest of your questions.
Dr. Marcus Price. We're running a bit behind, so now we're going to have a short 10-minute intermission. Please note the SRC have set up a stall. They're selling cakes and everything, and they'll tell you all about it. We have a raffle over at the back there. Hands up. Yep. And also we have the Astronomical Society over here. And for those who are looking for the restrooms, they're out the NPC to the left and around the corner. So we'll all meet back here in about 10 minutes. Thanks.